Hey, hi guys. So this is the video for the rest of the April examination. I did the term 1 stuff last term, just because it was useful to do. And now I'm doing the term 2 stuff. Yeah, so there's about 15 questions in this test that I'm going to go over. And I'm on a time limit because I've got like stuff to do in like an hour. So, busy, right? But yeah, so hopefully I should be able to go over everything. Hopefully you guys find this helpful, and yeah, let's get to it. This is it's kind of annoying because I accidentally deleted my last recording, so I guess that's how it works. But anyway, let's start with question 3 here. Okay. So ignore that; that'll come later. All right. So question 3. A firm's short-run cost curve at any given level of capital K is cost is equal to alpha k plus beta k to the power of negative a half q squared, where alpha and beta are positive constants. Which of the one of the following statements is not true? The short-run average cost curve is alpha k over q plus beta k to the power of half q. This is true, okay? Because we calculate short-run average cost by dividing the entire short-run cost curve by the quantity. So you have the short-run cost for each unit in there. Each short-run average cost curve meets the long-run average cost curve at a point where they're tangential. This is true. So if we have a long-run cost curve that looks like this, you're going to have a lot of shorter, let me just do them in another color. You're going to have a lot of shorter curves that are just tangential, sort of like this. Yeah? Hopefully that's clear. Okay, so you're going to have stuff like that. Yeah? So, we then go on to the next one. The long-run average cost curve is the envelope of the short-run average cost curves. This is true as well. They're all nested into each other. You should have just seen that. But D is where it gets incorrect. The long-run average cost curve passes through the minimum points of the short-run average cost curve. This isn't true, and I'll show you why. Imagine a segment of the long-run cost curve here, okay? And I'm going to draw a shorter run cost curve in it. Say it is tangential just about here, but then curves down before coming back up. The minimum of the short-run average cost curve lies here, whereas the tangential point lies here, above the minimum. Therefore, this one is incorrect. We also know that E is correct from that, so our answer here is D. But just for posterity, E is correct because it is the derivative of, well, the partial derivative here, of C with respect to Q. So if we derive C with respect to Q, okay, we eliminate the AK because it doesn't have anything relevant to it, and we use chain rule on the Q, which gets us 2 beta k to the power of negative a half q, and that's that. Okay, moving on. Let's move on to question, I think it's 9? 9, there we go. Now, this one you guys should remember just from rote repetition. For EX is a special type of when it comes to the Maclaurin series, where it is valid for all values of X, really. All real values at the very least. So, X element of the real set is correct here, okay? I won't go too into this and how you actually get that, but EX is pretty much one of those cases where it's not really bounded as much. Okay, moving on. No, that was a bit quick, but yeah, I'm in a sort of a rush here, so sorry about that. Which of the following is the trigonometric form of the number minus root 3 minus I? So let's try to solve this by plotting the actual number on the complex plane. Okay, so here we have a complex plane with the real component and the imaginary component. That point is going to lie, I believe, here, okay, where you've got root 3 over this way, and then you've got negative I, let's just go negative root 3. Okay, so we've got it there. Now for this trigonometric form, you need the modulus and you need the argument, really. That's why you call it modulus argument form, often. Here we can tell the modulus is just root 2, it's 2, so we can eliminate C and E. And then looking at the angles, we have a choice between pi over 3, minus pi over 3, and minus pi over 6. Now, it can't be pi over 3, because pi over 3 goes upwards and goes to something like here. So that can't be it. It could be negative pi over 3, or it could be negative pi over 6. But given that negative pi over 3 actually just goes here, it's not going to work, is it? So it's going to be negative pi over 6. okay, which makes it D. Okay, so that's that. We can also use this format for the next question. It says in the next question, what is the value of e pi I? Now, if you remember Euler's theorem, which is e pi I plus 1 equals 0, you already know this, but just for posterity, let me show you guys. So, if you remember, in this form, okay, the number in front of e represents the modulus, or how far away it is from the origin, and the number that, or the angle in radians next to I is the levels of rotation. Okay, we can see that we have a modulus of 1, and we're rotating 180 degrees around. So we rotate from here, which is 1, okay, all the way around. So this will get us to this line, which, surprisingly enough, is -1. So what you get out of this is -1. All right. You always want to think of these questions as sort of like rotations. I think it's easier to think about it visually if you sort of use that. Of course, it's always your preference. Okay, this one. This is where I sort of got stuck last time because I stopped the recording instead of pausing it. Okay. How you find a particular solution is quite easy. So say we have, and I think I'm going to get up my sheet here. This is the formula sheet I used for the last test. I think it is still up on the chat. Anyway, but we're looking for this one here. So we have the general solution for a difference equation, which is as such. Okay. And then the general solution works with this. So first we have the particular solution, which is shown by b plus 1, b over 1 plus c, and we have the complementary solution, which is a negative c t. Okay. Looking at our question, okay, let's actually delete that. We can see we've got 6 for c, and we've got our entire b is 24 over 2t. So what we're going to do is we're going to do 24 over 2t, like this up here, over 1 plus 6. Did I do this wrong? I think I may have done this wrong. Oh my god, I hate this. I have done this wrong, haven't I? Or is it just 24? Should be 8. Yeah, should be. It is C, but I'm not entirely sure why. Okay, I'm going to pause the recording this time and check. I have returned. Okay, as far as I can tell, I'm still not sure this is actually accurate. But, oh god, I've highlighted it now. Today's just been a mess. But yeah, what I'm seeing so far is that when we're finding the particular solution, you want to find just a form, which we're going to use a 2t here, because you can see the final bit is in 2t. Also, that excludes a, b, and e out the gate. So we put that in, and we're going to put that in alongside our other values, but for yt plus 1 and yt and stuff like that, we're going to put t plus 1 and t next to it, just respectively. So we're given the following: that, and then 6 t, and then a 2t. Okay, which is equal to 24 2t. Now, as far as I can tell, because we can see that you've got at 2t, those are, or t, hold on, ta 2t plus a 2t plus 6ta 2t. Oh dear, that was terrible. You can see that you've technically got quite a lot here. Okay. And what I think was this, because this sums up to something like 8, right? This sums up to like 8 A's in total, really. I think that's why it's 3 to the 2t. Because like there's an 8, lots of it. I don't think I have my calculations right. I don't know what's happened. Have not done this in a while, so I guess I've got to practice this. But yeah, it's definitely C there, mostly because you've got the addition sort of here of all the A's adding up. So there's like 8 A's, 8A 2t, and 24 2t, And so that leads you to the a is 3. So you've got the particular solution of y is equal to 3 at. Okay, moving on. That one was kind of a mess. Sorry about that. The differential equation there. Okay, so we've got a differential equation here. Right. Now, if you guys remember from differential equations that there's a specific form to some differential equations, if I can bring it up. But this one is a homogeneous one, thankfully. You can see that because we've got a second order one, and it's easily we can easily phrase it as a quadratic even. So we have m squared plus 4m plus 5 here equals 10. Okay. And so what we would do here, because we've got two separate roots. Well, actually, hold on. What did I do here? Oh my god, I'm losing the plot today. Hold on, I need to pause again. Oh my god, I hate this. Okay, I'm an idiot again. To find the stationary solution of such a function, all you need to do is replace y with, I don't know, just k, let's say. So if we replace y with some kind of constant k, assuming we have a constant here, then we have 5k equals 10. But given the k is a constant, all our remaining derivatives just equal 0. So we have equals 0 and equals 0. So k is going to end up equaling 2. Okay? So that's our stationary solution. It's just 2. So C is correct for this one. Okay? The difference equation is, however, quite different. Okay? For a difference equation, the stationary solution is simply just the product here. So you can see that it's just going to be ending up, I think it's 1. Is it 1? Just need to check. Oh, that's my old further maths book, by the way. I bring it out sometimes just because, like, sometimes I get stuck. Yeah, it is A. So what you do here is you just add them all up, and then that pretty much does it. So you set y as, like, some constant, and that will just set across the others. So you end up with just 1 plus 4 plus 5 equals 10. Basic stuff, right? Okay. Moving on. We now have a 2x2 matrix with eigenvalues lambda 1 and lambda 2. Which one of the following is equal to the trace of A? Okay. So if you guys remember what trace is, it's going to be the sum of the diagonals in a matrix. Okay. So I believe the answer for this is A. Oh god, hold on. Sorry, I'm just super tired. It is A, yeah. So, the answer here is both eigenvalues added together. Now, why is this true? Now, the trace, alright, let's just look at that. So imagine if you were just a regular, like, matrix, okay? And we've got the eigenvalues sort of being put in here. Okay, so we're going to be minusing those lambdas, essentially. Okay? Okay, also it's not none of the above, because that's just going to be not really working. So let's just say we've got 4 random numbers here, and then for these two we've got the minus here, right? If we're doing trace, then that means that we're just going to be adding those two, surely, right? Yeah. But wait, that doesn't work. Hold on. I hate, like, stopping all the time. Okay, to be perfectly honest here, I'm not entirely sure what's happening. So I would assume, okay, you would pick A in this scenario, because trace is essentially the addition of the diagonal bits. Okay, so if you're adding those diagonal bits on the matrix, then you are hypothetically adding it together. It wouldn't be magnitude, of course, because trace doesn't have any bearing on, like, the magnitude of it. And it wouldn't be multiplying because you're not multiplying those bits. So I assume it would just be A, but I can't figure out a way to prove it. If any of you guys can figure out a way to, like, prove that it is A in this, then I'd really appreciate it. But right now I'm kind of stumped. Anyway, 19. I've got to finish this in 23 minutes. I have wasted an hour. Okay, so for 19, you're asked to give a characteristic polynomial. In this case, if we're putting in the eigenvectors, you get a matrix of, well, not the eigenvectors, the eigenvalues. We get a matrix that looks like this. Doing the characteristic polynomial, we multiply these two, and we get lambda squared. Okay, and then we're just minusing the timesing these two, which just ends up 0. So we just end up with this. Okay, so the answer here is B, and if we check the answers, that is correct. Okay, then we do this again for 20. A lot of this last stuff is also based on dynamic systems as well, so just get ready for that. The matrix here, the eigenvalues are which of the following pairs. So we were just given this, so we know that our eigenvalues are determined by this polynomial. It's really just 0, okay? Because this equals 0, the only value this can really be is 0. So it's going to be 0 and 0, which means it's going to be E, which is backed up, as you can sort of see there. Okay. Then we have our final 5 here. Hopefully I can explain this in time. The characteristic polynomial of the 3 by 3 matrix is so lambda minus 1, lambda minus 2, lambda minus 3. Which of the following statements is not true? A is diagonalizable. Diagonalizable. Now, diagonalizability has no bearing on this so far. Hold on, let me just get up the thing here while I continuously talk to you so as to not make you bored. Diagonalizability. I'm just searching here. No. Oh god, it takes so long. Where is it? Alright, hold on, let me pause it. God damn it. I'm just jumping around, aren't I? Here we go. It is on page 618. So, we can see that on 618 it says, the n by n matrix A is diagonalizable. The general solution to 28.2 is that, yeah. So, the three following have to basically say this. So we have eigenvalues. Alright, that can be represented in this. Okay, so we have to have something that. Yeah. Hold on. What the hell? There's a lot of information here. Sorry, I'm just trying to work my way through this. Yeah, so if we have something diagonalizable, alright, we've got to have linearly independent eigenvectors here. Yeah, that's the main thing. Linearly independent eigenvectors. Now, we don't know if this is not true or not. Okay, remember this statement says which of the following is not true. We can't determine if it's diagonalizable or not, but we do know that there are three distinct eigenvalues. Okay, so we can maybe say this also references D. A is not necessarily diagonalizable, which is also true. Okay, this is also true as well. Okay, so what is the answer here? I forget. 21. It is D. Yeah. So, oh yeah, okay. So A is diagonalizable here, okay? So these three things back each other up, okay? It has three distinct eigenvalues and has three distinct linearly independent eigenvectors, but and that means it is necessarily diagonalizable because it has these three distinct vectors for a 3 by 3 matrix, okay? The determinant is also 6 in this case as well, okay? Because you've got those, like, imagine it's a 3 by 3 matrix which is essentially zeros on the side, and you've got 1, 2, 3. So it's going to be just 6 going down like that. And so yeah, because you've got that sort of matrix, something that maybe looks like this. I'm not entirely sure, but I think it would. Something that looks like this, it is completely diagonalizable because they're distinct, essentially. Okay. Alright, the characteristic polynomial of the 2 by 2 matrix is that. Which of the following statements is true about the general solution? Now, I'll show you this here. So let's first of all find those eigenvalues. So for this, you would get... Alright, you would get something like that. And then taking out the 3 lambda there, you get just that. Yeah, so you would end up getting 3 lambda minus 1, 2 lambda plus 1, and then this gives you the value of lambda of a third, and negative a half. Okay? So putting that into what we would have for our general solution there, we'd have something that would have a e third t plus a e half t. I'm not adding in the vectors or the constants yet because I'm just sort of modeling this. And we want to look at stuff. So we have a lot of this here. First of all, it won't exhibit any oscillations. Okay, this is because it isn't complex, so we wouldn't be using cosine or sine in any of this. Okay, this means it's also not none of the above, really. Okay, well, we don't know if it's not none of the above yet. The magnitude of yt tends to infinity as t tends to infinity. This is not necessarily true. Okay, as you can sort of see here, it kind of doesn't. So if t was to tend to infinity, then, well, technically speaking here, the e there would just take over, wouldn't it? So would it tend to 0? This is true. It does tend to 0, because the magnitude does not tend to infinity in this case. Let me show you a demonstration, okay? This red line, oh, ignore the green line here. This red line sort of shows how that would progress, okay? Obviously, the x would show the t, so as t moves on, you would assume it moves to infinity. See, the thing here, yeah, hold on, is true about the general solution. It is 22, right? Yeah. Hold on, what is it? Yeah, it is A, yeah. So yt, which is this whole thing, tends to 0, really. But it's like, this is just like, God, I hate this. Okay. Which one of the following statements is true about the general solution of yt of the difference equation yt ayt? So if yt tends to 0, okay, as t equals that, so that's sort of just going to be like a constant diminishing, essentially. And I think that's right. But it's like, yeah, because there's this like tiny little thing here. Yeah, so look, B is false, mostly. Yeah, so it's more like A is like process of elimination, because B is false. B is false. Why? Because this little section here, it's slightly declining for this little section here, okay? So as t sort of progresses, the magnitude of yt doesn't be like that. As t progresses, it does dip. You see here? So it can dip as well. So B isn't possible, I don't think. Something's wrong here. I can't tell. You know what? Never mind about it. Let's just go with the other stuff at this point here. Okay? So what we're going to do is we're just going to do the last three now. I think this is sort of it. Sorry if I can't give super detailed things, but I'm sort of just like tired, and to be honest, I can't really do everything here. I'm going to be revising these just to check like where my gaps in knowledge are, but this is sort of like my thing as well. Anyway, let's move on from that. Moving on to 23 now. Can I clear the whole canvas? There it is. Alright. The 2x2 matrix has eigenvalues 1 plus I and 1 minus I. Which one of the following statements is true about the general solution? Now, you need to put it in modulus argument form for this, okay? So the modulus argument form here, we've got 1 plus I, that's going to have a modulus of, well, if we think of a 1 by 1 triangle, it's going to have a modulus of root 2. And it's going to be going up at a sort of like a 45-degree angle. So we're going to have pi over 4, I believe. So we're going to have cosine pi over 4, and then plus I sine pi over 4. So like that. And then for obviously the conjugate, we're just going to minus it as well. So we'll have cos pi over 4 minus I sine pi over 4. The usual. Okay. Now we want to determine if it has alternations or oscillations, okay? And if it's explosive or dampened. We can tell, because of this thing, okay? It's root 2. This has a R value higher than 1, okay? So the oscillations are going to be explosive, okay? And they are definitely not going to alternate, okay? Because we don't have, like, yeah. It's not really going to be an oscillation. What's the difference between oscillation and oscillation? I should have revised more. But it is oscillations in this case. It's going to be explosive, all right? They're going to oscillate because you've got those trig functions there that's going to essentially do that for you. But yeah. Yeah, God, how do I put this? Yeah. Yeah. Because it's not going to alternate. Alternations, what does alternations mean? Hold on, I just need to quickly check this. I'm sorry that I'm just like cutting away so much, but it's just like, I've really got to check. Right, I found out. Also, terrible webpage, because it's like, oh, these two things are synonyms. That's absolutely a lie. Absolutely a lie. Hold on, where is my... There it is. So an alternation will change sign every time, and a... What is it? Yeah, an oscillation will not change sign every time. So it's an oscillation in this case, because, let's see here. Yeah, so you've got these eigenvalues which essentially just like bump up above it. And because you're going to have like this explosive, yeah, you're going to have explosive level, it's going to start above, isn't it? Because you've got that start of the difference equation that's above in its essence, and it's not really going to like change sign every single time because it starts above it. I think. Oh god, I'm such an idiot. Oh god, okay, I really need to like focus on this. But it is explosive oscillations, okay? The at least you should know that the R shows it, so it's explosive like that. Alright? I'll look into this a bit more. If you guys want to ask me questions, just feel free to text me, and I'll try to like figure out the details. Okay, 24. Let's get on with this, because I've only got like 9 minutes now. So, this should be easier. Alright? Now, all you really need to know, in this case, is the eigenvalues. Okay? So we have this matrix here. This will give us the characteristic polynomial of 1 minus lambda, 2 minus lambda. So we have this. This surprisingly gives us 2 minus 3 lambda plus lambda squared. Okay? Or if you want, you can just look at those values there, because this gives us lambda values of 1 and 2, respectively. Okay? Now, if you look in further dynamics, no, just further dynamics? Dynamics, just dynamics. Or dynamic systems? I think it's just, yeah, it's just dynamic systems. And you look at the attributes of each different type. So you've got sink, you've got source, you've got spirals, all that good stuff. Okay, where is it? Trying to flick through the pages. There it is. So starting on page 631, you can see that there's different types that you can get from different, essentially, yeah, different values. All right. So if we have positive real roots here, which is shown by like 1, 2, here, this example is literally on page 630. You have a source, okay? And a source is also otherwise known as an unstable node, so you want to pick D in this case. I have heard that Pemberton does like to reuse questions, so this is a case, okay? If you're having trouble, just like see if this question actually exists, and then maybe you'll get it. But yeah, you want to look here for basically what's your roots of the characteristic polynomial, okay? Because if they're both positive, you've got a source. If they're both negative, you've got a sink. If you've got different sides, you've got a saddle. Complex with positive real is a spiral source. Complex with negative real is a spiral sink. And then pure imaginary is just center, which is cool, I think. Anyway, moving on to the final question here, number 25. If the 2 by 2 matrix has eigenvalues 1 and negative 2, the fixed point at the origin of the differential equation is one of the following. It is a saddle point, because we've just mentioned, as shown on page 633, that if you have complex roots with opposite signs, you are going to get a saddle point. And if you guys just want to verify that, 25 should be C. There it is. Okay, sorry for a somewhat disorganized look at that test. I'm going to hopefully try to put out formula sheets sometime in the next few days, just to help myself and help others, I suppose. If you guys have like slightly more detailed answers, feel free to post them in either chat or like I'll share them around or something like that. But yeah, hopefully that was helpful. Yeah, I'll upload this probably tonight. Oh my god. Anyway, hope that was helpful at all, at least for the dynamic systems at the end. I know I'm kind of a mess, but sorry. But yeah. Okay, I think I'm done now. Alright, hope you guys have a lovely day. Good luck with the revision. And yeah, hope you guys get good grades. Alright, bye.